per centimeter, 100 microsecond, 8 pulses, 1 hertz to 5 kilohertz. This is all I need. How long it takes? Someone time it. Takes 10 seconds, maybe 20, maybe 30, maybe 1 minute, maximum 1 minute. Okay? I time it because I had to be correct. EGT, come on. Okay, did someone time it? How many seconds it took? Okay, this is all I need. I don't need anything else. Huh? And then number 3. What is the steps in formation of electropore? I need the ECT concept. Okay, what is the concept? Application of external application of external voltage. I know here I am going to get short, but you know what I am talking. Okay, so A is external, B is charge accumulation. Okay, because due to no conduction, all that. See, I have written everything. Okay, due to no conduction, capacitor effect of cell membrane, due to hydrophilic and hydrophobic bilayer phospholipid layers. Okay, so I have written everything. I don't want to write here just to save time. This is what. Okay, I want you to understand and reproduce. If you understand, you don't have to memorize. It will be nicely stored in your hard drive. Okay, so understand. That's why. Versus number 3, voltage build up. Okay. Number 4, what is it? D is very high E field development. So I will put here, okay, E equal to V over D equal to 1 volt over 10 nanometers. I put all that. Okay. So this will take some time. Okay. So that's why 9 programs, 30 minutes. Easily you get 3 minutes per. You need only 1 minute to 1 minute here. You save all that time here. Make sense? These are the steps. Questions? Anyone has any question? Okay, number 3. Number 4, I know that is challenging now. Number 4 and 5. Number 4 I was expecting. Remember, you have your membrane. This is inside, cytoplasm, outside the cytoplasm. You apply the voltage, charges will accumulate because it cannot conduct. Okay, so bilayer, all that, phospholipid, all that you write. Apply the voltage. Okay, and then drug molecules outside. So you say that these are drug molecules. Okay, so I have written all that things, and then apply the voltage. Okay, and then you apply the voltage, E increases, pores open, drug molecules enter. Okay, so I put this like that. This is the concept, ECT concept, ECT process. Okay, here yes, I expect E equal to all that. Okay, if it's 0.5 volts over 10 nanometer, or you can use 1 volt over 10 nanometer, all that. Very high. Okay, very high voltage gradient, membrane breakdown, opening of pores, entering of drugs. Make sense? So you just whatever, everybody knows this, correct? It's only you to transfer it to the paper. So if any problem, please correct it now. So in case if it comes tomorrow, you should be able to ace it. When I repeat the same question, if you don't do well, I will take up lot of points. Okay, here see, I cannot give you final exam makeup. This one you can still do makeup. You see the difference? Questions? Okay, and then the 5th one, sketch. It says sketch. So I use that. Remember, I didn't draw the hand and all, but that's what we will be doing. Okay, so I just use the simple one. Okay, drug molecules outside. This is your cell. Okay, and no drug inside. application of pulses, okay. Drug molecules go in, some stay outside, okay, and then potent effect. Okay, the drug is concentrated in a small area, so effective or potent effect, okay, potent effect of tumor, pain reduction, volume reduction, everything. So drug inside the cells, localized potent effect, okay. So first is chemo drug outside cell, application of pulses, okay. I have to mention what pulses. So I have mentioned here 1200 volts per centimeter, all those things, okay. 100 microsecond 8 pulses, 1 kilohertz less 5 kilohertz. Then electroporation happens, EP, electroporation, potent localized effect, tumor treatment. Make sense? Questions? Okay. 6 is there? Yeah, that's a great question. Maybe I need the board, I will erase it. And the 7, how many of you got the right value? It should be 0.34 or 0.333 microns. We sell diameters, we talk in micrometers. Micron is micrometer, so you have to convert everything, okay. So very few, but still you didn't get the right, you got 333 some of you got, yeah, you got it nanometer, but it should be 0.33 micron. Some of you got 250, I don't know how you got 250, the values are simple, no. We will do 7 first, 8 we will discuss, because 6 I need the board. 6 we will skip for now. 7 is what? V equal to 1.5 E times R, or 1.5 E times diameter means D over 2, correct? So it will be 3 over 4 E times D. So D equal to 4 V over 3 E, correct? You have this equation, actually I gave it. 4 times 0.5 is 1 over 2, correct? Divided by 3 times E was how much? 20, no? 20 kV per centimeter. So this goes 2 and then 2, this one 10. So it will be 1 over 30. kV is 10 power minus 3, okay? So the centimeter goes here, and this 0 I can take 1 over 3 10 power minus 4 centimeter. 10 power minus 4 centimeter is 10 power minus 6 meter, correct? 1 over 3 is 0.33 micron, that is the diameter. We talk diameter of the cells in microns, 10 micron, 20 micron to 0.3 micron, it is really small cell, okay. You will get around 10, 20, the hot cell is around 150 microns, okay. Anyway, this is to get the calculation rather than the next time I will give a right value. Make sense? How do we do? This is a simple equation. D equal to 4V times over T. The challenge here is converting kV to centimeter to everything to microns. The answer is in centimeter. We have to modify everything to that.
Ma'am, from where this formula came?
Oh, there is a big derivation. It is, remember, it depends upon the frequency and all. So they simplified for DC. Dr. Swan, H.P. Swan, he developed this. He is also considered father of, electrical manipulation of cells. Dr. Zimmermann did lot of experiments in Germany. These are all contemporaries, okay. Dr. Zimmermann is still there. I think Dr. Swan just passed away 2-3 years ago, okay. These are all giants in the field, okay. Giants mean giant, real giants. They are all invented, okay. So I have this one, actually I brought it to show it to you. We did this is an undergraduate project, okay. We have what is called independent study. So the student, if he likes to work with some professor in their area, they can register for 3 credit hours and they can do, okay. So here he did it electro manipulation of biological cells. Okay, Hassan calls them. This was done in 2004 when I was in Arizona State. If you see the equation for, this is the equation, the membrane voltage is the big equation, and then you assume the resistance is negligible, this and that. For DC you can bring it to that form. So he did varying the impedance, varying the omega t, the frequency, this and that, MATLAB fully, the whole thing MATLAB. Okay, you see. So obviously he gets A for this course. So some professors don't, some department heads don't allow because they think it's an easy A. But people like me, you give enough, I have no problem giving you D. Again, I can publish it. I haven't yet published it because I always keep some things for future. If I don't have anything and I need to publish something, I can go for it. You can take this, the whole thing. How can you copy? Take a picture of this one after, and then you can repeat it. Maybe we'll work. We can do more work. We can write a paper along with him because we have to give credit to him. I think he went back to Saudi Arabia. He was from Saudi Arabia. They give scholarships sent to Purdue and Stanford, and they get back and then they do well. So that's what it is. Okay. Any questions so far? And then explain the rational need for ECT. This should be everyone should get all the 13 points. Who can explain the rational or need for ECT? When do we use ECT? Very good. Okay. Especially for inoperable, radioresistant, chemoresistant. Okay, correct. That's what I written. When the current standard of cure, including surgery, radiation, and chemo, do not work or patients do not respond, it's called refractory. Patients do not respond or cannot be applicable. I told you, if you have a heart disease, who will do your left side operation? Who will apply radiation? No one. Okay. We need an alternative, safe and effective, physical, affordable technique. Towards this, ECT is a boon for inoperable, radioresistant, chemoresistant tumors due to its very physical and simple nature, suitable to all histologies of cancer, especially solid cancers. You see, I covered everything. Make sense? Anything else? Okay, now let us go to ECT versus IRA. Okay. I know I am borrowing some time from the pulse generator. I hope it's okay. No, because 9:30 we have to talk the pulse generators. Because my goal is whatever you learn thoroughly. Instead of learning too many things, you learn one thing well, and the rest, you have all the slide. You can learn at your leisurely. So ECT versus, whenever I say compare and contrast, draw the table. Okay, first comes the mechanism. Okay, ECT is electrical pulses plus low dose drag. Okay, here only. Okay, because I have 7 points. Okay, second, what is the magnitude? Here you can just click the photo after I am done, you don't have to copy down. 3, what is next? How many pulses here? It's the frequency. Here almost the same, they can use anyone. It's not standardized. You can put 1 hertz, you can put 5 hertz. It's not, people use various values. Application. Applicable to all solid cancers. it is called, okay, histology. Histology is the word the pathologists use. Histology means the nature, okay, whether it is carcinoma, adenocarcinoma, melanoma, sarcoma, okay. So, all types histologies, okay. So, histologies is the plural, okay. Sarcoma, sarcoma means tissue, okay, tissue, bone, it comes, they call sarcoma. If it comes in thigh, it is a sarcoma. Breast cancer is a carcinoma, okay. Carcinoma means epithelial cell. Epithelial, epi means outside, correct. Epithelial means that is the most outside cell. Inside is endothelial cells, and then comes the surface muscle cells, okay. So, sarcoma, carcinoma, melanoma. Melanoma is skin, okay. What else? Lymphoma. Lymphoma means lymph nodes. Lymph nodes are there, they are like the drainage of our system, okay. They take the dirty water, according to my language, and take it and clean it, okay. Lymphoma, sarcoma. Leukemia is the blood cancer. And then bone cancer is myeloma. Multiple myeloma is the bone cancer, okay. So, myeloma. Okay, I know we are not supposed to be experts on this, just I am telling in case if it registers. Okay, applicable to all solid cancers, ECT. What about IRE? Currently, that is what, remember, it is still developing. Currently used for advanced, inoperable, irresectable, stage 3 and 4 cancers. Which ones? Pancreas, pancreas number 1, liver, stomach, of course prostate cancer. Prostate is the most common, okay. So, they compared to pancreas and prostate, this is the deadliest, though it is most common for women. Breast is most common, for men this is, okay. But you know, we can know it from the swelling, so we can treat it, okay. And many times they say wait and watch, because sometimes not giving, remember, all the swelling does not become cancer. 30% only become cancer, we do not know which 30%, so we treat everybody left and right, okay. There was a study, okay, if you treat 10,000 women for 10 years, okay, mammogram, okay. So, you take once a year mammograms, that means 10,000 times 10 means 100,000 mammogram you take, 720 false positives, okay. Then 27 death, and then some thousands of biopsies, you know, because lot of false biopsies, false positive, false negative. 2 lives were saved, okay. To save 2 lives, we have to treat 10,000 women for 10 years. Each year there will be false positive, there will be biopsies, there will be lot of going to the hospitals, mental agony, anxiety, depression, distress. But who knows, that 2 life can be you and your mother, or I and my mother, my sister. So, every life matters, correct? That is what we do, okay. So, many times they wait and watch. If you are above 60 only, they do something, okay? Up to 60, 65, wait and watch, because many times you will die by heart attack in 62. Why bother to treat prostate cancer? For women that is little less, because though both men and women die, cardiac is the number 1 death reason, women die little later. You know, the longevity of women is more than men. So, there are a lot of jokes about it, anyway, we would not talk about it. Men have to be strong, otherwise say bye bye and be happy in the heaven, no? That is what I always think, maybe we are going to a better place and happier there. Why should we be afraid of leaving this place? Anyway, questions. So, does it clear everything ECT this one? So, tomorrow everybody is going to ace it. Okay, so you know how the emotions affect what organ, ECT, the medical devices, what is that, muscle stimulation. We talked a number of times. So, I hope you can take all that and study tonight, and then thank you. So, we will start, no, we will start our pulse generators. One is Arizona where I was, this is where I started my work, and then now I moved to Purdue. Okay, so I put this one. You know, in the beginning I didn't have access to cells and all, so I started only software. Okay, I had very good students. I talk about this, they will come and tell me, I want to work with you. I will say, I don't have money, that's okay, we will work with you. And okay, so I had many master's theses. We just study lot of MOSFETs, IGBTs, you know, by varying their rise time, fall time for a given circuit, how it works, what is the output, like that. Okay, so initially I did lot of software, computer studies. Then I got someone collaborating. Then I started all the cell studies, and now I am working with the medical doctors, working with patients. Okay, you see the evolution, computer simulation to in vitro to in vivo. In vivo I did my some in Chicago to humans. Okay, this was my first. Yeah. This was the first paper. Cheney, Alan Alton Cheney, he came. He was doing masters at that time. He's a mathematical major. Okay, we take anyone with 3.1 GPA at that time in Arizona State. He's a electronics technician working for Motorola. Okay, very good fellow. Electronics is his breath, is everything. He loves math also. Okay, so I talked about it. He said, why not I build something? So he built this simple MOSFET based high voltage nanosecond pulse circuit. So I don't know about you, in 2004, okay, 13 years ago, we published in 2004, means we would have started before that, correct? Nanosecond pulse is still a new thing, nano things are just upcoming. MOSFETs are, you know, remember normally 10, 20 volts, now they are coming in hundreds of volts, okay. Those are all big issues. And then now they are coming in thousands of volts. Okay, still remember all these electronic device, MOSFET, IGBT, transistor, everything is delicate darlings. Okay, so we decided, okay, to build a nanosecond, because I know the BTX, the pulsar I use can give microsecond and millisecond pulses. Okay, so I needed something for nanosecond, so we thought we will build that. Okay. And nanosecond is not used in clinical trials, not to treat humans, but it is useful. Many people just for the word nano, I think they use it. Okay, they get funding also. Okay, they study, because remember it is capacitance, correct? Membrane is capacitance. If it is very high frequency, okay, remember 1 over 2 pi fc. F is very high, what will happen to the impedance? It will be like a 0, you know, 1 over 2 pi fc, F is very high, xc will be 0, it will be a short. So what happens, you apply pulse to the cell membrane, the membrane offers a short circuit, you go directly into the cell. So they are thinking to go and utilize the nanosecond pulses to attack or to attach receptors to mitochondria, because mitochondria is responsible for a lot of heart issues. Okay, so they are trying to work, you know, you attach, in addition to the molecule, you attach receptors which will guide it to go and sit where you want it. Okay, because our cell will contain mitochondria, you know, Golgi complex, nucleus, nucleolus, you know, all that. So we can direct them. Some people are even talking about attaching okay, magnetic nanoparticle. From external you apply a magnetic field, the particle will go. Okay, for breast cancer one professor was doing, now he is retired, maybe he is doing more now. Okay. So, we can use this for, in addition to electrochemotherapy, gene therapy, research in ultrasonic cleaning, chemical free bacterial decontamination, medical imaging. The bacterial decontamination only we saw that lemon juice, okay, because we can kill them without, normally they use heat. Heat is not always the best. It is called non-thermal because thermal is not at all good anyways. Okay. So, the circuit was designed to drive. Okay, this is another thing take home. You always keep the impedance 50 ohm resistance, because you don't know the cells will have different, the body will have different, the tissue and humans will have different, but we need a standard. So, typically you consider a 50 ohm resistance load and then you vary it. Okay. So, this is the standard. Okay. So, in this case we wanted to do a 1 to 400 volt 75 nanosecond okay, pulse generator. And again like our ECG, EEG, it has 3 stages. Okay. One is the you know pulse width, you generate the pulse width. Second one is the driver stage for the MOSFET. Third stage is the delivery of the pulses. Okay. So, in this case he calls it integrated variable frequency, variable duration pulse width signal source. Okay. But we did not vary much, we vary the voltage, we did not vary the pulse width. And then inverter driver stage, you know, no, the MOSFET needs a driver. Everybody remembers your electronics, correct? MOSFET, IGBT, transistors, drivers, all that, control circuits. And then power buffer consisting of a passively loaded single power MOSFET. Okay. He, you know, he really took the pains, he bought the things from eBay to save me money, because you know we were using our own money and his knowledge, his time was not paid. Sandeep, this is what you have to do, you buy ISEX. This is the, at that time this was the state of the art MOSFET, okay, radio frequency MOSFET. Now they have changed. Okay. This is 400 volts, even 2010, 2011 we bought like 3000 volts MOSFET and all. Okay. They are costly, but that is what we need. Okay. You see the amperes, 16 amperes. Okay. Discharge current, 6 nanosecond rise time. Okay. Very sharp, very good. These are the ones we need to use, okay, for if you want to do electroporation work. And then these are the technicalities, I do not know whether we need it. This is what again, okay, I will show you. We need a 50 ohm resistors, he did not have a 50 ohm, he had 150 ohm, he put 3 of them in parallel. Technically that is correct. Practically what do you think? You have external, you know, additional connection, additional this one. So, I told him we could have bought like that, he said no, we do not have time like that. Okay. So, this is the kind of students we need, who is proactive, who thinks about everything, okay, and who, okay, everything almost he did it, we only had minimum discussion. Okay. So, he took the 200 volt nanosecond pulse and he wanted to see, you know, what are the frequency components, so that he can design, he can pick the components accordingly. Okay. So, you do the MATLAB analysis and then he found out what is the, you know, the highest component and all those things. And then these are the 3 stages. Okay. 5 volt pulse generator, and then you do the inverter driver, okay, raise it to the pulse generations, pulse you know, control, and then high voltage. Okay. So, these are the stages, nanosecond scale pulse, output stage driver, okay, driver is the controlling of the MOSFET, then the output stage, okay, 3 stages. And then here is the first one, the signal source, driver and output circuit. Okay. So, he uses a 300 ohm variable resistors, 15 kilo ohms, okay, IN 4148, I think you know all these diodes, and then the capacitor is 150 picofarad. Okay. So, you do a design before you build it. So, he did all the design. If you see this paper, you have everything, you can reproduce it. Okay. And then he used the schematic concept, okay, and then that will go this is the symmetrical concept, this is the driver which will go and on this MOSFET which will discharge into this. This is the MOSFET, source of the MOSFET. Okay. We used the auto transformer for a 0 to 400 volts variation. Okay. Everybody knows auto transformer? Again, he had one from somewhere, he brought it. This is the whole schematic. Okay. And we call it novel because at that time it was really novel, it is very simple, there's just 3 tape, economical, we only spent $1,000, okay, $1,000 is nothing. The MOSFET itself costed a lot, okay, cost list is the MOSFET, MOSFET based high voltage nanosecond pulse generator, okay. So, I think to know every individual component is difficult, so all you have to know is that you need a signal source, nanosecond pulse source, you need a driver or controlling stage or pulse forming stage, okay, and then you have an output stage. Typically if you see it is really simple, if you want to know the concept, everyone knows exponential pulse, forget about that, everyone knows capacitor. So, you charge a capacitor, what will happen? So, you have a DC charge, okay. Charge a capacitor and then discharge it. So, what will be the waveform? Correct? It will charge and then it can discharge. So, it is very easy to make an exponential waveform. But I told you, in the beginning they were using exponential for gene therapy. That is when the doctors got really annoyed of this technique, because remember E times T equal to constant K. In this case, if you want to increase the intensity, automatically the tail will be increasing, okay. So, when you increase E, T also increases. So, lot of killing of the cells. Though it does not matter for gene therapy, some doctors did not like it. I remember in 2003, yeah, I was in Johns Hopkins, that is where I got my training. I met a doctor, I was telling her my work. I said, the minute I said electroporation, oh, too much killing. I still remember vividly that reaction. Then I had to explain to her, no, that was olden days, now we have a square pulse, we can vary the intensity, we can vary the duration, but once you have a mindset, it is very difficult. That is the problem with doctors. And I would not blame them, because they are working with the humans. So, they want to protect both the humans and themselves. If you try something new, something happens, who is going to answer, the family or your conscience? But still, if you are like that, then we could not have come to this level, correct? Then we will be still in the ancient stages, we started with surgery and radiation, then chemo. So, we have to keep moving, okay. So, that is what it is, okay. So, charging, okay, discharging, you can get all you need is a pulse forming network. If you see, I will show some of them, that is what they do. They charge and discharge a capacitor and then they use cables, transmission lines, okay. So, as it propagate, you form the pulse, but they will not be exactly square wave, they will be something like square wave, and that is good enough to do the work, okay. So, pulse forming circuit they will call it, okay. So, this concept is simple, charge and discharge and form the pulse shape, okay, control it using MOSFET. MOSFET is a very good device for controlling, because it is high speed, but of course low voltage, low current, which is good enough for us, okay, for our applications. Make sense? Okay, so I am giving the concept. This is the pulsar he built. We did lot of work, all my juice work is done from this one only. This is the 3, these are like a military grade resistors, they will withstand very high heat, okay. Ceramic, Sandeep, this is ceramic resistor, okay, we do not use it normally. But for okay, in the lab you use carbon wound film resistor, you cannot use that. You use a high quality, everything should be the best quality, okay. and you see everything he put. This is a ground plane, he put everything on a copper sheet and grounded properly, okay. Prototype with ground plane and solder mount or surface board PCBs, okay. Transmission line construction. So, this is the back side of the board, okay. Then we measured it. So, you can see how nice, in 2004 70 nanosecond, this accurate is not much heard of, okay. People will build, there will be lot of undershoot and overshoot, okay. So, for all practical purposes we got a very nice square wave. Typically there will be inverse, okay, it means negative, okay. And then so here the input was 408 volts, the output was 394 volts, okay. And then horizontal scale is 25 nanoseconds. So, if you calculate per division, so it is okay, vertical is 50 volts per division. So, pulse width is about 70 nanosecond, the fall time is 10 nanosecond, okay. Waveform, this is how you write, okay. You take a scope picture, you put, you show all of these values as much as possible, and then you give description also. The concept is, without this writing, this should give us all the values. Without this figure, we should get all the values, okay. They should be complemented. That is how you write a paper, okay. When you write a paper, you describe, you just do not say figure 3 shows, no. Figure 3 shows da 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 da, and then you can see there is 3 resistors, 150 ohm connected in parallel to get, you have to explain everything, because an 8th grader should read and say wow. That is the only response we need from a audience, wow. Anything else, they couldn't, they shouldn't ask what is this, what is that. Everything should be explained like a palm of your hand, okay. I used to say like your mother smile, you should do it like your mother smile. Some students tease me, oh my mother never smiles, she is always grumpy like that. So, since then I tell like your palm of your hand, okay. So, I want you to be thorough, whatever you do it should be first class, okay. Questions? This is how to write a paper. This is another one, we found it in the literature, they used it, okay, in University of Southern California, okay. Again if you see they use the same MOSFET, okay. This is very fast, 2 nanosecond rise time, okay. It was rated for 400 volts 40 amperes, okay. Remember 40 amperes is normal, pulse means we can go easily 5-10 times, okay. Pulse current into 10 ohms load, these people put 10 ohms load, okay. So, this one they used it as a pre-stage for their amplifier, okay. This will be the driver for their further stage, but however this is good enough, this generates nanosecond pulses. So, we took this and we simulated this, okay, using PSpice, MATLAB, and the, yeah.
How earlier was changing the magnitude?
How?
You have mentioned that
It's a variable, you know.
Earlier, you mentioned that it was changing the voltage from 1 volt to 400.
Yeah, we had a auto transformer, that is our input. So, you vary the auto transformer, you know auto transformer, we use auto transformer.
But MOSFET required DC.
You can do the conversion, he did all that, we did not show that. Yeah, there is lot of work going on, I am giving the concept. Okay, so we build that one also. Then comes, okay, this is the pulsar we started in 2009 and we finished in 2010. Again it was a class project, the student took it really interest, and I showed this one, no, the alternate Chinese project. They said we want to challenge him, we want to build a higher voltage and lower nanosecond pulse, okay. Remember high voltage, smaller nanosecond is very challenging. So, they went for 1000 volts 25 nanosecond, okay. They built 35 nanosecond, it worked out, okay. So, this is again 3 stage, I will show this 3 stage and come back, okay. You have a high voltage source, pulse generation, nanosecond switching, okay. So, again this is the 3. So, we have a 9.6 volts DC rechargeable battery operated, okay, that is a 9.6 volt DC source that will be outside. Variable pulse potential magnitude of 0 to 1 kV, and then variable pulse durations, variable pulse repetition rate. Okay. Two master students did this work. Again, it is really very compact, 4 inch by 4 inch, okay, that is the width and length, 2 inch is the thickness, okay. You can put it in 4 inch, everybody knows 4 inch by 10 centimeter by 10 centimeter by 5 centimeter, that was how precisionally they built it, okay. They took it as a challenge, and I get from, even as last week I got an email from all over the world, we want this circuit, can you build it for us? I have to say sorry, my students graduated. I didn't even collect that PCB layout. So people ask, give me that. I don't even, I just believed them, they just vanished. In future I have to collect everything, okay. So this is the 3 system blocks, okay. High voltage source block converts the 9.6 volts to a variable high voltage output of 1000 volts, okay. And then the pulse generation block generates a short nanosecond pulse, okay, which is like 35 nanosecond, supplies enough current to adequately turn the MOSFET on fast enough to apply a nanosecond pulse into the load. We use a 50 ohm load, okay. And then the nanosecond switching block is a MOSFET based low side switch that applies, okay, short pulses into the load, okay. So pulse generation, high voltage source 9.6 volts to 1000 volts, and then you generate a pulse and then you switch them into the MOSFET, that is it.
Ma'am, but where we will apply this that load must not be equal to
No, we just build it and then we apply to the this one and all. We studied cancer cells and fruit.
This pulse duration will be for 50 ohm load.
Yes, that is the standard. Then we apply. There will be some distortion. We don't worry about it.
Then pulse duration will be changed.
Yeah, yeah. We see when I test the cells, I only care how much is the, how many cells died, how many cells live. Once you standardize, yes, when you vary the load, the pulse will vary. At that time I don't worry about the pulses. I am interested in the results. This is to prove that it is working, okay. And then I applied to juice. We did lot of juices, strawberry, mango, orange, lime, lemon, everything. This is the $1 million circuit, okay. Actually we should have 3 stages. Anyway, I used to have 3 stages, I put them all together. This is the high voltage portion, okay. And this is the pulse generation portion. This is the switching portion, okay. So ultimately these 3 will give rise to, okay. If anybody is interested, you can borrow this circuit, you can build it. And so they did a PCB layout and I should have gotten it, many people could have benefited anyways. They are not in touch now, that is the problem, okay. So this is the top and bottom layer, I will show, they put all the passive elements in the bottom so that they do not talk to each other, okay, they do not touch each other. So you have to route it properly, you have to have the narrowest width and then the shortest pulse, so that otherwise every PCB, that copper layout will become an antenna collecting this one. We are talking 35 nanosecond 1000 volts, okay, that is a very difficult combination, okay. So this is the top and then this is the bottom layout, okay. We use it, the capacitor was like in farads, we normally use microfarads, so farads means, okay. So this is a 3000 volts capacitor, okay. And then the MOSFET, again we use ISEX, I have the report, so we can do that. Again you see it is not perfect, but this is good enough for all practical purposes. So you have a 1000 volt output pulse waveform, you have the scaling and all. So basically we got almost the desired values, okay, 25 nanosecond, and then the shape is not good, but we are happy with that, okay. So here is the capacitor, you can see that the capacitor is the bulkiest and the costliest part, 3000 volt capacitor we have to buy. and then your MOSFET is sitting here and the rest of the circuit. Okay. So, yeah, they took they did it in for the grade, and then they made it more better to write the paper and all those things. Okay. So, nanopulsar, you see this is what it is, 4 inch by 4 inch by 2 inches. Okay. And when we presented in the conference, people cannot believe it. We showed it. We took the thing and we showed it. Okay. People were all awing. Okay. How can you build it? That's why I told you, everybody wants this circuit. So maybe if some of you can build it, we can make money.
Auto transformer is as shown in
Not here, not in this. Here he used 9.6 rechargeable battery to 1000 volts. Auto transformer is the other one, 2004 400 volt nanosecond, 75 nanosecond. This is 2009 1000 volts 25 second nanosecond. We grow up in 5 years. Oh, I moved from Arizona State to Purdue. This is different, that's different. No auto transformer, they use 9.6 volt DC.
very 0 to 1000 volt varying voltage will need some variable voltage technique like transformer or etc. EMCO battery, EMCO, the control resistor. The resistor will do a lot of losses. How they convert it? They use EMCO F50.
This is the 9.6 volt to 1000 volts conversion. It's DC converter. We can vary that 9 volt battery, we have a DC power supply, you vary that will vary, okay. This is separate, we kept it outside, yeah. Oh, but yeah, that 4x4 doesn't include the DC power supply, it's separate. We couldn't put everything there. Yeah, you're right, yes. That was separate, we connect it to the, the table there, and then we use it like how you use it, your function generator. Yeah, that one is there. But still, how many people can build this? 4 inch by 4 inch, okay. So we studied using, you see, fresh lime and mango juice. Okay, we applied 496 volts. We use that cuvettes. You remember the pulse generator I showed you, there were cuvettes, okay, there were 4 millimeter gap, we used that one, okay. In this case we applied 500 volts, okay, 0.4, same, okay. Again, this is how to report it. Yeah, we have a paper, and then this is another my review paper, okay. This paper has got 38 citations, and so someone asked me to write this, so I did it, okay. We did some electrical modeling of the cells, okay, and then if you see, remember at high frequencies, the membrane is a short, it will go into the internal. At low frequencies, the membrane offers impedance. So this one, okay, this is how we validated our model, okay. Using our model, we could draw this curve, so we can show that at low frequency the membrane comes into plane, the high frequency the cytosol, the inside of the cell comes into plane, okay. So we did all that, and then we studied a lot of other concept. This is what it is, okay, charger. Just like here, you have a charger, and then you discharge the charge voltage through a transmission line, okay. Basically you put cables in parallel, okay. The length of the cable and the parallel number of cables decide, okay, the ZO, the characteristic impedance, and the time constant of the wave, okay. And then you have a spot gap which will fire, and the output will be sent to the impedance, okay. So it's called Bloom line pulse forming network, okay, PFN. That's what in Germany and in US, in another school they did it, okay, but because they wanted very high voltages, like these people do, you see, 300 kV per centimeter, okay, 10 to 300 nanosecond, and then another one did 4 kV 5 nanosecond, okay, and then 10 kV 5 nanosecond, okay, and then 4 kV 5 nanosecond, ceramic bloom line mini pulse generator, water bloom line, okay, they will put it in water to change the resistance, so that change the impedance, change the the change, and then inductive added charge cable, so they do many ways, and then again 400 volts 5 nanosecond MOSFET, microscope, okay, I will show this one, okay, and
10x
then
load means what?
10 times the load,
10 times?
10 times the load impedance. Remember the impedance of your this one should be higher than 10 kV 10 nanosecond. This one is I think maybe Mr. Zimmerman built it, okay. And then 15 kV 11 nanosecond pulsar, 15 kV 45 60. Yeah, these two are that Zimmerman. He is supposed to be the father of the electroporation, okay. So he built it. Shall we finish this and take a break? That way then we can discuss, okay. This is what is called the microscope pulsar, microscope based. You see here, you have that microscope and all those camera and everything, okay. You put this the pulsar in here, okay, connections and all will be outside. It is called cover slip, it is a glass slip, it will be square like 2 centimeter by 2 centimeter, okay, and with these are two of the electrodes. In between is a 0.33 millimeter gap, you put the cells there, okay, and then you put the cover slip so that if anything happens they do not flash over, okay, stainless steel electrodes, and it is a slide, okay, they take the blood and all, the slides, that slide, okay. So that is a glass, and then this is called a chamber, okay. You put a small like a like a trough, like a tank. So you put this in here, you apply the pulse, and you observe the variations as you apply the pulse, how the cells vary, how they die, you can record everything, okay. So that is what they do. They want to see like when the pore opens, when the pore stops, all that they can do many things. University of Southern California, okay.
Treatment technique, you have written pulsar.
Yeah, I was interested in the pulsar. They use that, remember the first one I showed you?
But there, here it is a pulse already is coming from somewhere.
Yeah, this is a treatment chamber, okay. See the this is inverted microscope, okay. So that will come, you apply the pulse, this fellow is in here, okay. Apply the pulse and observe all the variations happening in here.
So this become a treatment chamber.
Yeah, this treatment bit we can treatment cells to study the nanosecond effect. Again you see the gap, 0.33 millimeter is the gap, okay. So they apply 1000 volts. If you apply 1000 volt divided by 0.33 millimeter, what is the value? It will be 300 kV per centimeter. That is how they get 300 kV per centimeter. They do not generate very high voltages, okay, because that is why I told you which doctor will be happy to use 300 kV and all, okay. So this is how they do, but 0.3 millimeter, which organ can you treat? 0.3 millimeter. These are all so far in the text, in the paper. No one has been treated using a nanosecond pulse, okay. So if you see all my work, I used this for research purposes. I use the millisecond and microsecond to treat patients, because it is not easy to build a pulsar and it is very costly. Oh, we did not talk IRE versus ECT, right?
We have talked.
No, we did not finish it. What happened? We'll go back there later. Yeah, I didn't talk all this, okay. So these are all more nanosecond pulsars, okay. So this is the pulsar, this is the setup which we showed the schematic. Maybe we will come back and do. Okay, with this we will stop. Any questions? We take a break then come back.
Yes, sir.
Where were we? This one, no, this high voltage pulse generator, that is this fellow. Per centimeter microscope and everything. They use the 370 volts 30 nanosecond. Okay, 370 volts across 0.33 millimeter. What is the electric field? 370 volts across. Now some of them use like 100 micron, 0.1 millimeter. That's how they get. Okay, you put 100 volts across 0.1 millimeter. What's the field? 100 kV per centimeter. No? This is how they do. How can we treat patients with the 0.1 millimeter electrode? Okay, so we have to do lot of scaling up. What happened? Others didn't come. Iron hasn't come. Who else? Only iron. Oh yeah, Rahman. What happened? They are not coming. Anyways, maybe we can discuss. I think I showed you. One more thing I have to show you. Not here. I will. Okay. This is the charging circuit, which can be used as a nanosecond pulsar. Okay. And I have a review paper written. It was invited and. So, you can look for nanosecond electroporation, another look. So, this one gives you everything we talked, all the references and more. Okay. I will be talking about the effect of nanosecond versus microsecond pulses and then the various nanopulsars. Everything is here. This is from here. I didn't put all the waveforms, but everything I talk is in here. So if you want, you can take the picture of this. It's there in the Google. Nanosecond electroporation, another look. With this, I will formally conclude the lectures. Questions? No, we had some talk outside. Okay, I will tell you. Anything regarding pulsars, if anyone want to build any term, we can work on it. Okay, this one, I will look.
Pulse variation ranging 1 volt to 400 volt has some problems.
Why? It's 0 to 400. He put okay.
Because MOSFET or whatever you are using,
you will have some correct.
voltage rating, and it will not work below the threshold voltage.
Correct. But who is? Why would I build a 400 volt pulsar to apply 1 volt? That is just figure of representation.
Just you are saying range, na? That's right.
Okay, yeah, that's fine. Yeah, you can. Yeah, that and okay, good. I will change that. But that is the true thing. I don't know what to change. That's fine. See, that opens up questions like that. So that's good. Okay. Number 5 was applicable to this. We are talking ECT versus IRE. Okay. Applicable to all solid cancer. Currently used for advanced, inoperable stage 3 and 4 pancreatic cancer, liver cancer, stomach cancer, prostate cancer. Okay. People are talking about using it for colon cancer, colorectal cancer also. 6 is economics, cost. So, no, the ECT is really cheap. I was told, in Bombay and all for electrochemotherapy, one session they charge 35,000 rupees in private. Okay. Of course, if you go to government, it is cheap, or maybe you have to pay 500. I know in Pennelam in Chennai they charge, okay, it is a non-profit, they charge 5,000 rupees. Okay. ECT they charge like 12,000 rupees per sitting. And if you do not have money, they call me and I normally give 10,000-20,000 because you need two sittings. So I want to promote this. So from there I will ask my sister to give the money and I will pay her. Okay. So how costly is nano knife? Yesterday we discussed about it. Not only the nano knife is costly, okay, hundreds of thousands of dollars, plus you need to have CT scan, you need to have ultrasound mediated, tumor finding, and then all that, okay. Then operation theatre, no drug, remember? IRE, no drug, but you need a surgeon, you need an operation theatre, everything, okay. But of course, you want to save your father-in-law, and then money does not come into picture, but it is costly. Seventh thing, effectiveness. How effective? Okay, can you discuss compared to ECT and IRE, which is more effective, or are they same effective, or one is less effective than other? Effectiveness. From whatever you heard, from whatever we learned so far, how do you compare? Is ECT better than IRE or IRE better than ECT?
ECT is better.
Why? How?
Effective on it won't.
It is simpler and yeah, we have more cases. So far it looks like yeah, we do not need to correlate our heartbeat with the application of pulses. So overall yeah, ECT gains because it is more prevalent, but we have to wait and see, maybe we can make higher.
And also drug delivery, it should not be affected.
Yeah, the drug delivery will add on to it. Yeah, if you have a yeah, there we go for curative. Okay, palliative can lead to curative in ECT, whereas in IRE it is purely palliative. So you know the difference. But yeah, we do not have a cases. But people, I told the pancreatic patients live 10 to 22 months. It is like a real life. They got a new birth.
For skin cancer, etc., we can use nanosecond.
Nanosecond pulse? Yeah, you can use. You can use anything. It
No,
has to
actually
work.
Inside our body's organ, it will be somewhat difficult. But on skin cancer and
Nanosecond pulse is costly. It is not yet
yeah,
proven.
costly it is, and
It is not yet proven. Not yet proven. So yeah, you can use. See, I am for patient. Anything works. I one way or other I have no inhibitions. I do not have a closed mindset. Okay, if it works, be my guest. Remember, one size does not fit all. Any therapy will not fit all. So there will be always room for another therapy. You can use nanosecond pulse, millisecond pulse, microsecond pulse, picosecond pulse. The sky is the limit. Imagination and research. Application, different ball game. Okay. Sandeep, where are you? You are supposed to be very active. You are still dreaming or sleeping. You did not speak at all.
In this electroporation, ECT aspect, one thing is gene therapy also we are doing.
Yeah.
One aspect.
Yeah, I need to do. Remember, now we are running out of all the medications, okay, chemo drugs. There are what is called drug resistance. Then we cannot do that. So cancer gene therapy, if you see, there are 1,000 gene therapy trials are going on. 60% is cancer, but still again, it's still in the bench stage, not come to bed. Yes, yeah, even I want to do it. The problem is, I do not have anyone to collaborate who knows more than me, because see, I want to know which gene to put to treat breast cancer. So, there are too many genes. So, if I do literature, so I need someone to tell me do that. Worst case, toss the coin, pick one and do it. That is what I am going to do.
Actually, when compared to IRE, which spoils that cell, here we are introducing a good.
Yeah, gene therapy has real potential. That is going to be, they are talking about personalized medicine. Then you find which gene is affected, you go and rectify, repair it, kill it, whatever.
Nothing will happen to the cell.
Yeah,
Just you
nothing. Yeah, we will have a lower thing. Yes. Gene therapy is the next chemotherapy. they say it's the next thing. Yeah, I want to work on it because especially siRNA, it's a small interfering RNAs, they are small ones, like they only have 20 to 25 nucleic acids. They will be considered as a good alternative for chemo, okay, whenever you cannot use chemo. If you are
Very still, everything is very highly.
no, we only need to know which pulse parameter.
Type of G.
Yeah, once you know which.
The gene, you need very precise to access the gene.
Yeah, again you have to attach something for the gene to go. Yes, there are some.
What were the side effect it is
Gene? In gene therapy, so far we envision none. You go and replace the existing gene or kill the bad gene and put this gene.
No, it might have some
Long term effects not known because we haven't done it. Huh? Yes, it's very good question. Long term effects unknown because
mutation can happen. I mean,
it's okay. Why do we worry about future? Today is we live. Tomorrow who cares? Correct? Today let us today is the day, let us enjoy and be thankful. Tomorrow when you sleep, we have in Tamil, uranguvathu polam sakkada means night sleep is a temporary death and death is a permanent sleep. Correct? Sleep is temporary death and death is permanent sleep. That is true. So don't think too far away.
probably we were not aware about future. That's why today we are getting. Otherwise, earlier, if people were aware, then cancer would not happen.
No, cancer was there even 4,000 years ago. That the Persian queen had it. She had her slave to cut her breast. Remember those days, no anesthesia, nothing. Okay, poor fellow. Normally they give drinks so that he became sedated and intoxicated, not sedated. Still there will be pain, correct? So I don't know how it was done. But remember, the willingness to live makes you to suffer that. Imagine cutting that too. The knife, I don't know how sharp it was. You should read all, read that, emperor of all maladies. You will get a grip of, how these doctors are. I am so happy these doctors in the 1930s are still in 2016 the same. They don't welcome new things. Okay, they teach it in the medical school, I think. So it's the same closed mindset. You have to break the barriers open, which we are trying to do. Some doctors do, some doctors don't. That's what, see, I am working on a short film. I said, I have my disc here. This is my $40,000 information here. So some doctors oblige because they see the patient, nothing is working, they cannot leave like that. Patient from Delhi, Calcutta, everyone comes to Chennai. This Dr. Rajini Gupta, she is really an angel. She will try everything. She is so nice. Dr. Kalavadi, like that and all. They are so good, so good. So we need like that many people. So you carry the flag and go and spread this technique. Whoever has it. That IRE, it's not done in India. You have to go to US, Louisville, Dr. Robert Martin. And there is another doctor in Florida. Only 2 doctors are doing it in US. And I think in Europe and all they don't even do that. They do only ECT. There is a second World Congress on ECT, electroporation and electrochemotherapy in September in US. So you are all welcome to attend. You will learn a lot about this technique.
We cannot find video.
You can. Why difficult? You have some.
To present paper.
You don't have to, you can attend. Only thing you need money to buy the ticket and to pay for registration. They even have 1-day registration. It's okay, you never know, you get a contact there, that's worth your 1 lakh rupees. It's worth more than that. Yeah, otherwise let us, if anyone wants to collaborate, let us work. It is every 2 years. It is only, they started 2015 in Slovenia, 2017 in US. I don't know where is next one. Maybe I will volunteer 19 in India or at Purdue, whichever works. In India, how many will come?
We will be definitely.
Yeah, not in Kharagpur.
Not Kharagpur, in Delhi, Mumbai.
Chennai.
Delhi, Chennai.
Chennai, that is my only place I want to go. I can eat freely. But I don't know, yeah, maybe. That's why you all should come attend and you should say, we want to take you to India, then they will oblige. If I ask, they will say, take you to Purdue. That is also okay, at least I can save the flying and rooming charge, still I have to pay the registration. So, we will see, yeah, I will go and talk to them and I will ask for, bringing to India because, I gave a talk, they had another conference, bioelectrics, I gave a talk. They were all very happy that it is in India because I showed that 2 patients, remember, in that. They said, oh, it is in India, they are doing it like that. So, India has a very welcoming market for any business including medicine, ECT, okay. They will have tons of patients here. So, yeah, maybe I will ask for India. If they say no, I will ask for Purdue. Otherwise, maybe they want to go from continent to continent, okay, they let them decide. I am not in the board, I did not become because, it was all full of Europeans, I said go, maybe I can become part of it. So, everybody knows what is ECT, IRE, EGT, then ECG, EEG, EMG, muscle stimulation, medical devices, including what are the various medical devices we saw?
ECG, EMG,
Vein finder, non-invasive blood pressure measurement. So, that is what we will do in the afternoon, correct? PPG leading to blood pressure. Not just PPG, what do we do with just PPG? We have to use. That way, someone should work on how to get the glucose, blood glucose using PPG or something. Or it does not matter, you just get some blood and put it. That put it should be real easy, so that maybe, yeah.
But for diabetes patient, that coming also
It's a problem?
it is like wound.
Oh, it wouldn't. Very good. So, now all the more we need a non-invasive. God.
Ma'am, nowadays they are using sweat to calculate.
How accurate?
no, ma'am, 82% is maximum last by found literature till 2016. He is working whether there is patient is within diabetes or not. He is working with that. I have added one thing is that if the spectrum change with the glucose concentration within blood, I will work with it.
So, how accurate is yours? Sen, you
We
never.
already developed the hardware
Okay.
with the help of different kind of IR generator.
Okay.
The signals.
Okay.
And right now we are
Signals from where?
patient fingertip is sending somewhere receiving
Okay, sending what wave?
from 0.7 nanometer to 1.4, 1.5 till the
Broad area.
broad
How
area.
do you send that wave? You have a device?
Yes, ma'am. That he has developed in hardware sector. Developed
Is it what a LED or
LED and
LT and
and
I and LT and not
I?
we are using both physical spectrum as well as the near
IR.
infrared as well as the IR.
Okay, IR LED.
Entire spectrum.
Oh, that's what yesterday someone was talking, no? IR and this one.
Spectroscopy analysis.
Okay, so how accurate?
not tested yet. Just developing this.
Okay.
One girl from Malaysia, she has developed a nano, antenna, giving a transmitting wave and receiving. How much receiving spectrum is there? Based on that, she has predicted, and nearly 80% she is correct. But no one achieved more than 90% till now. So,
Can you send all those details?
yes.
Otherwise, Raman, what's your work on? Oh, you are going to
Our
join.
major problem is the patient, number of patients.
Major problem, India has thousands of millions of patients, 60 million patients. But yeah, you need to get a doctor who will work with you. I talked to, Dr. Manjunatha, in medical school? He works with many doctors because he is working on that, remember the PPG, this and all. So, I told him about your work.
I told you about the phonocardium heart sound.
That is why I told him. So, it is easy for you to get a doctor in Kharagpur or in Calcutta, not in Chennai. So, contact him, you know him, Dr. Mahadevappa. Manjunath, Manjunath is his first name, Manjunath Mahadevappa. And he is in the School of Medical Science and Technology. Where is his boss? Tell him, contact Sanjay. What happened? You are not in the, you are still tired?
I told him. You were there, na? You were there, na? At that day. And yeah, that is
And
only.
your measurement technique,
Yeah.
both you will be compared.
You know all
For
this.
example, whatever it is the
He knows him?
Yeah, actually he forgot that.
Yeah,
That's the reason.
I talked with sir with different problems.
Yeah, talk to him to get because he only, I told him about it. I told him that I was going to talk to
Too much
doctors.
interested to work with non-invasive procedures, and you already introduced one new thing, ECT. I am very much interested about that. We will together work with that. It's very nice.
that you can compare and your technical.
Yeah.
That also can be done.
Not that. I mean, this is the report. Can I send a mail to you?
You can compare with your
Calm down.
Is taking microneedle. I mean, you won't feel that blood is going
Hmm.
very small. I haven't taken photos of that circuit where we had made it.
What about your partner? Doesn't he have?
He also didn't take.
Then I had to deduct points because everybody will have this.
I had to make piece by circuit. Based on the amount of piece by circuit that he has developed.
I know,
That
but
is
still.
microneedle. That is not.
Yeah, you get 90 anyway, so you should be fine. You will get 90, you should be fine, I said. 90 is the highest, Yeah, I have to take print because you need that, this one. I was telling to take, okay. Oh, what about homework and all? So, tomorrow is the last day. By the way, maybe you finish everything tomorrow, the final exam, because that is 30%, then we can work on, okay. Either you give me or send me all your thing, maybe I have to save somewhere and delete it, because my email will be fully loaded. So, yeah, homework 1, I think everyone turned it. If you didn't turn it 1. Tomorrow is the last day for everything. After the exam or we have to do evaluation, we will do after the lab today evening. That is the scheme. I need 4 homework, okay. 2 are lab, 1 is your dream device, 1 is the first one, okay. So, I have to grade all that. Quiz I will give you grade tonight, so that I know maybe this evening before I make the final exam, because if you did not do well I will give the same question again, okay. Otherwise study well, okay. We will leave by 5 today, so that you can study, prepare well. Now also we will disperse by 11:30 until 2:30, you have 2 hours, 3 hours, 11:30, 12:30, 1:30, 2:30. So, yeah, eat 5 minutes, okay. One day you have to eat because you need energy to study. No brain cells won't work unless you fuel it, okay. How the car needs petrol, brain cells need food. So, some of you think you are very busy, you do not eat, it will reduce your efficiency. So, always eat well, especially exam and all, eat well, come nicely. Okay. So, do everything, finish the exam 9:30 to 11:30. Then by 2 o'clock turn in everything, or I will prepare as this one, I will tick, I will tick and put a mark. You can show me your laptop if you do not want to send all that, okay. So, you are ready after 11:30, until 11:30 we are officially. And yeah, I know I am yet to grade, I will grade today, tomorrow, okay. Yes.
This blood sugar glucometer, what principle do they work?
They take the blood, the blood will have what is that, lipids and this and that, I do not know exactly, but we can find out. So, they calculate the cholesterol and everything, and then they calculate the glucose in it, the content in it. So, there is, yeah, I see we have that meter like $30. The problem there, I bought it because I want sometimes I want to eat something, then I am afraid. So what's my blood cholesterol, glucose will be. So I bought it. You know, they have some kind of needle to prick. That fellow is not working properly, so I have to ask someone to prick. Whenever I prick, no blood is coming, maybe it is not hitting properly. Okay. So I thought if we can find what happened if I take a normal pin and prick it, maybe I should do that. So, but the strips are costly, but I was told in India in medical stores for 20 rupees we can. So I want to do that, maybe daily I will go and measure it, that way I will know. Yeah, I want to.
And the prickers nowadays good prickers have come.
Yeah?
You have numbers 1 to 5.
Oh.
If you are unable to prick on 1, you can go for 2. You can increase.
Okay,
and
so
at 5
there
it
are
definitely pricks, and then it's so fine. 30 gauge something it is.
Okay, someone if you are already read, go to the medical store, buy that for me, I will pay you, then maybe we will try tomorrow. We will measure everyone's glucose. You are all young, you can eat.
One touch that is 1500.
Yeah.
The latest one.
Okay, how does that? It also it's easy to prick.
In 3 or 4 seconds the reading comes.
Okay, what it's called one touch. I want to buy that then.
One touch. You go to any. It's a small unit like this. A quarter of this. Then there is a place to insert.
That is also
Acu.
Prick.
How much is that one?
To 1 second or 2 seconds the droplet comes. Press. Just put it. It gets sucked.
Really?
3 seconds it comes.
So is there a shop here we can buy?
We have medical stuff here.
Shall we go tomorrow and buy? Tomorrow is it open?
It is better today, I think. Tomorrow is.
Okay, tomorrow after the. That's why I said tomorrow, because you have to study for exam. No. So we can go this evening, 5 o'clock. We will do the evaluation and we will walk. I will buy. Okay.